I will start.
Guys, please, let's watch.
Okay, today I will give a little seminar about the work that I was realizing the month there in Japan. There is like a little overview of Feshbach, the Feshbach theory. That is what they make there. They work with ultra cold atoms, so they wanted to apply quantum control techniques for this technology. So I will make a little introduction to the Feshbach theory and everything. I will give some insights, and this work is only I made it there in Japan and I start to make it here, so it's in a really preliminary results, but I will give you like a little bit of the idea and where it should go. Okay, the line of the talk will be first, I will present the experiential paper. It's the paper that they read and they say, okay, maybe that apply shortcuts in this like probably works really well, and I will be like a little brief introduction because I will come back later. Then I will present the ultra cold atoms really briefly because it's a huge technology that more or less everybody hear about, that speaks about a really popular technology. Then I will enter more in Feshbach theory, Feshbach resonance, Feshbach molecules, and Feshbach ramps. That is quite interesting. And I will explain a little bit and give a really overview. Also, it's a really big topic, like there's novels and everything there, so like huge topic. And finally, the quantum control techniques that we decide that can work well in this problem and how can adapt it and how can be like, the idea is that we want to make this like we can use the quantum control techniques to experiment, not only simulation. So how can we adapt everything to an experiment? And finally, a little bit the perspective of the work and where we want to go. Okay, the paper that they presented when I arrived there is Observation of Collectivity Enhanced Magnetoassociation of Lithium in the Quantum Degenerate Regime. When I read it for the first time, I didn't understand really what they want to say. But the summary is that they have like a quantum degenerate gas, a Fermi gas, that is formed by lithium, atoms of lithium. So what this works about is if you apply a magnetic field to the degenerate gas, you can form molecules of lithium. So if you have a gas of lithium only atoms, you have a Fermi gas. But if you, with this magnetic field, you can change from a Fermi gas to a bosonic gas, and all the properties change completely, and you change from a fermionic gas to a bosonic gas. So, okay, the platform that we work, like the technology that they use to study all these things are ultra cold atoms. Ultra cold atoms are gases or systems that cool down to a really low temperatures, to close to 0 Kelvin. For this, they make laser cooling and a lot of advanced techniques. That what they make is like try to dissipate, like to remove all the atoms, all the energetic atoms, and with a laser they slow down, they remove also the kinetic energy of the atoms. What is interesting about cold atoms is that if you cool down a lot, the nature of the systems stops to be like particles and start to appear or be more important the wave properties of the systems, because you are close to the Broglie wavelength of the particles are comparable to the system, to the interatomic system. So all the quantum properties are much bigger, like you can observe it better, and they are necessary to explain everything. Also, really interesting about this is that they are really controllable. You have a lot of control of all these technologies, so they are really interesting to make quantum computation, quantum sensing, and everything. Like these, for example, are the laboratory that we visit in Toulouse, that they use cold atoms to make quantum computation. In one-dimensional traps, they use it to make qubits, to produce computation. And we are going to be more interested about physical interest properties like the crossover, superfluidity, etc. Like we are going to study the BEC-BCS crossover. Other properties of ultra-cold atoms are superfluidity. That is when you have really, when you are at these temperatures, the particles can move in the system without losses, and this is also if it's neutral atoms, it's superfluidity. If it's charged atoms, it's superconductivity with Cooper pairs and everything. Like it's all in the same box, more or less. So the study of these physical properties gives you insights of all these properties. So let's start with looking what are Feshbach resonance. That is what we are going to work. Feshbach resonance occurs when you have two particles with really low momentum, and when they collide, these particles stick together and form a molecule. Okay. To give like a small perspective of this, we can use the LED figure where you have two channels. The black channel is the entrance channel or the background channel, and is the potential that the particles, the two atoms, see when they are in the free state. No, there are two particles, and it's like the potential of the collision potential. And the red one is the closed channel. We are working with the intuition of one closed channel, only two channels, but the closed channel, there is not one. There is n closed channels because it is related with the molecular bonds. So you have like the red one is the closed channel. The energy is up the energy of the system, and then you have the background. This is where the normal system, the particles moving then around. So when we have the energy of the closed channel is close to the energy of our particles, free particles, what can happen is to jump to the closed channel, and they can form a bound state. Okay? What is the interesting thing? That this closed channel, we can control it, the energy of this closed channel, with a magnetic field. So this is making a tuning of a magnetic field. We can move the closed channel and the entrance channels to make it to make a cross between the energy of the system and the bound of the energy of the bound and form a molecule. This is the general idea. How we can control it? For control it, we have the S-wave scattering. That is the right equation. The S-wave scattering is an effective element that, because if you have an scattering, like we saw like in the bachelor, if you have two particles, if you have two systems, and you make a scattering, normally if the wavelength of the particles that you are making the collision is not small enough, you cannot see the structure of the other particle. If you have a really long wavelength and you want to see something, like you are not going to see the inner structure. Because in these energies, you don't have to use like all the scattering details. You can make an effective scattering properties. It's the wavelength, and use it like a ball. And all the properties are in this effective model. And this is the AS that you can see that have a lot of elements. The BG is the background, it is related with this channel, and then you have the dV delta, the delta V, that is the resonance width, and then you have the V0 is the point where the resonance occurs. The resonance occurs when this blue line and this red line are in the same. So when you can go to the molecule, like when these pairs can form a molecule. And this you can see experimentally, like how this experimental data, they meet in 2001, 2 or 3, that this experimental is correct. And then here you can see how the number of atoms decrease in the resonance points, and this it decreases because these atoms form molecules. Okay? So, okay, and magnetic field, you have how we can make molecules, like controlling the magnetic field. Because the most common way to make Feshbach molecules are with ramps. So you start, really easy concept. You start with a B, really big B, and you have the pairs of atoms, and then you decrease the V, you decrease the V, and adiabatically you form the molecules. Okay? It's adiabatic evolution, normal adiabatic evolution. Also, really cool and interesting thing is that controlling the B, you can change from a Barden-Cooper-Serfier BCS gas, like superconductivity and all this weak interaction and everything, to a bond stuff. So you have all the intermediate steps, so you can control it and you can make it like the reaction as you wish. And here there is two cool figures. That the first one, you can see how this is the atom cloud, and you can see how applying a magnetic field, you can form the molecules and separate in the bosonic cloud and the fermionic cloud, the atoms and the molecules. So you can see experimentally, because this is something that you can see. When we go to Toulouse, you can see the experiment, you can see the cloud, the atom cloud. And this is also like the from Fermi to, for Fermi to bosonic, the change with the magnetic field. You can see that you can confine the atoms because they have boson properties. Okay, so now let's come back to the paper that I present. They work with this Hamiltonian. This Hamiltonian is expressed in ladder operators, or fermionic and boson ladder operators. It's not the complete one, obviously. There's more interaction. There is like 3-body interaction and everything, but our idea is to extend it. But right now, this Hamiltonian is really common use and it works quite well. And it has 3 terms. The first term is the bosonic term. It has information of the bosonic number of bosonic, and delta T is the control parameter. It's our control parameter. It's the magnetic field. The second term have the information of is the fermionic term. Have the information about the fermionic energy, the cinetic energy of the fermions, and everything. And the last term is the off-diagonal term that has the information is about the transition between the fermionic to bosonic. And GC is like the term that has all the information of the system. They have the information of the scattering, of the chemical potential, of the trap, and everything. So what they claim in this paper is that depending how you ramp the speed and if you make it linear or polynomially, you can get more molecules. The fraction of molecules that you can get from the system is better. So depending if you make it ramps fast, slow, or polynomially or not, you can get more molecules. Because one problem of these Feshbach ramps is that you get like a 5% efficiency. So you don't have even efficiency because you have losses for inelastic collisions, you have a lot of ways of losing. So the idea is to design a control, so they design delta T, instead of making like they make polynomially or linearly or what they make polymerally, make a shortcut or make an oscillating field to enhance this performance. Okay? So yeah, here you can see, for example, for different alphas, this alpha 1, alpha 2, like depending on the speed, how if you go fast, like how okay, here they plot the speed of the ramp, this alpha, and the move. The move is if you make it linearly or polynomially. And you can see, like, if you go fast, the polynomial ramp works better. If you go slow, the linear ramp works better. The idea is like, you have like control, and depending how you make it, you can make it better or worse. And okay, so let's speak about quantum control protocols. I always speak about shortcuts. I will not go really in detail about counter-diabatic driving because I think that more or less here I explained tons of times about this. But general idea of shortcuts, for if you don't know about the theory, is that you will use like you want to make adiabatic process faster without you want to make an adiabatic process without the adiabatic requirements. So what you can make, you have to make quantum control techniques to be able to decide to make it faster adiabatic protocols. In our case, we are going to work with counter-diabatic driving. So the idea of counter-diabatic driving is to add an auxiliary term to your real Hamiltonian to avoid these diabatic transitions. Here you have the H lambda is the normal one, and then you have the gauge potential H lambda, that is the diabatic. The gauge potential is what the shortcut is, the shortcut. Okay. So for designing, you can use nested commutator, and you can calculate it, and you get this term. What happens? For simulation, this term is really good. You put it, and it will work. But if you want to make it to experiment, this term is something of the nature. It's not the magnetic field. It's the interaction. So maybe it's not. For simulation can be interesting, but if you want to apply it in a real experiment, maybe you cannot apply it directly. Obviously, you cannot apply it directly because it controls some nature properties. So the idea of Peter Claes is that you can use Floquet engineering for mimic the shortcut. What they say, you can make a stroboscopic driving of the Hamiltonian, and with a stroboscopic oscillating control of the Hamiltonian, you can mimic the counter-diabatic driving. So the idea is that this Hamiltonian, that is only your Hamiltonian with a control, and the interaction Hamiltonian, and this case will be the delta, the part of the delta that we speak before. This is the bosonic part. This you can control it. If you make a stroboscopic driving of this and this, you have the same that you have here. So using this Hamiltonian, you can mimic this Hamiltonian. So, okay. And how you can calculate everything? Pues you will make it, you can take your Hamiltonian, you can get from here the alphas, and then you can put it here like there's an equivalence. Like you have the Bessel function is equal to the alphas, so you can calculate the alphas using the normal things that we made, and then translate it to the Flockit engineering. Also really cool stuff that we saw is that here, like you have if you see the first order A lambda, the gauge potential first order, and the second order, they are proportional. They have another term, but they are proportional. So you can see that in the first order, the Lie algebra closed. So you don't have to go to high order to have expressivity. Like you don't have to take the nested computation spacer to the big L's to have a good shortcut. Okay. So the current situation now is that I'm making all simulation. I calculate the shortcuts. I make all the diagonalization part and everything because I just started about this. The insight is like it points to a good position, but right now I'm making the calculus, so I cannot present the simulation because I'm making now. But I also use this to present this cool technology, and if someone has some insight or want to know more about this, let me know. So thanks for the attention, and I hope you enjoyed the talk.
Is there any application for generating this kind of molecules?
Yes, a lot. The first one is study quantum properties, because the more for me, what more interesting is that first is something called cold chemistry, is how the molecules form and how all these condensates interacts. Also to see nature properties of quantum mechanics, because in this ultra cold this ultra cold stuff in the ultra cold regime, you can observe much better quantum properties. Also, superconductivity, like they are related. So if you control and you know a lot about these transitions and how the weak interaction, you can control better the Cooper pairs. There are some people that if you want to go to higher temperatures, you have to know about the mechanism better. There are some papers in neutron stars also that looks that they have this. So if you want to understand neutron stars, it points that there are some bosonic and BCS-BEC crossovers, and then control all these things like for quantum computing, quantum sensing. Like, I'm not an expert of cold atoms, but almost tons of people works in this. So there's much more application. In my case, only study nature properties and how to control it and everything. But there's a lot of applications, yeah.
So you mentioned that the Flockit engineering Hamiltonian is not like an extra term to the Hamiltonian, but it's equivalent to the whole Hamiltonian that you wanted to on the system.
The Flockit, what they say is that if you use Flockit engineering, what they observe is that the effect of effective engineering is the same or is equivalent. There's some details, but it's equivalent to the counter-diabatic driving. The problem, so the thing is that, okay, it's more complex because you have to make all the stuff, all the Flockit stuff, but if you want to apply it directly in the Hamiltonian, this will appear like oscillating of the magnetic field. You don't have to add other terms.
So at the end of the day, what you're controlling is only the delta.
The delta, yeah.
Only what?
The delta T, the magnetic field. Instead of mega ramps, we probably be like oscillating ramp.
Do we have this freedom to fastly oscillate the magnetic field experiment?
Yes.
You can.
The cool thing is that when I was thinking what shortcut technique to use, because I think invariants, no, really complex. Mean field stuff, okay, I have to look it. And everything, like create molecules oscillating magnetic field is something that is done. but in another completely different way. So this is something that instead of making one patch, there is other ways to produce molecules. And one of them is oscillation. I don't know the speed that you have of oscillation is something experimentally, but it's not like finally. I think it will be not something like, how do you say, something complex, because the magnetic field, like, you can control it really, really well. So it looks like you can make it experimentally.
I was thinking about what you're doing is taking the usual clamp and
Yeah.
then try to apply shortcuts to make the process faster. But do you think that you will also get better fidelities in the process, or?
The thing is that if you don't go fast, there's some things that are good if you make it fast, and are something that are bad to make it fast. What they observe is the normal ramps are not efficient, and you have to design it well. So if you can, a lot of losses comes from diabatic errors. So if you can reduce these diabatic errors, you will make better the transition, because finally it's a diabatic process. Then there is something that, frankly speaking, I have to check, because this is a really huge reduction of Feshbach theory, because they have, like, cannot pass from a single, like, there is also singlet, triplet, there is forbidden transitions. Then the S wave scattering is the first order of expansion, but you have P wave scattering, you have D wave scattering, so you have to take all in account. This will be probably reduce the diabatic errors. Let's see first how it works in the simple case, and if enhanced, and then I will start to put more stuff, because go fast is good, go fast also is bad, not only for the diabatic errors. There's more stuff about reelection of the saturation. If you go really fast, you have a saturation and everything. So applying shortcut looks well, because you will remove also, if you have a lot of time, the particles, like, interaction is really fast. With the collision, you will have more inelastic collisions, so you will have more losses. So that's an equivalent. Right now in this part of the, like, until I don't check it more and put more things, I cannot see if it will be much better, or the effort will be not worth it. Also, that they are working with really low transition rate. The maximum is maybe 34%. So maybe, like, it's not like it's ultra high that they have, like, ultra good experiment results, and it's impossible to arrive there. Like, they are really bad. So make something good, and that works probably.
When you said that your Hamiltonian had an stereoscopic term, what does stereoscopic mean?
Stereoscopic is like the magnetic field, like, you have this delta, no? So this with interaction, the d delta. So this is a magnetic field. Instead of make a ramps, you can make you can make delta, like, oscillate with a scene, like.
Stereoscopic in the sense of rapidly oscillating.
Yeah.
Okay.
One question about these operators, the B and the C. What is the meaning?
B is the creation operator of the bosonic field, and C is the fermionic. This B is a reduction that they make, because you can only go to the first molecule state. This im B is like creation of this.
Yeah, but I mean, what do you mean by bosonic and fermionic field? So of what? I mean,
The bosonic is the creation is like this mimics the creation of the molecule, and the fermionic, like, you have a fermionic gas, so you have, yeah.
so of particles or like of the fermionic lithium.
If you write the system with a second order quantity with ladder operators, you have the vacuum, and you create with the fermions with the C, with the fermionic operator, no? And you have, so the bosonic, what you express the system, like, you annihilate two fermions, and you create one boson, because you have two particles. So this is the relation. I don't know if I'm explaining well or not.
So this B is like a creation operator of those bound states.
Yeah, of the molecule, because it works like it's not a boson, it's a co-boson, but it's a boson. Like, depends on the details that you want to study.
I have several questions. First question is, so you always use this two-level system. So I wonder whether you can connect this atomic DC directly to the molecular DC.
What? Repeat, please.
For instance, you use the two-level system, which means that you will couple your initial state and final state, which are the atomic DC and the molecular DC.
Yeah, this one, not this figure. Yeah.
In some sense, you cannot directly couple.
Explain it better. I don't get your point.
For the Feshbach resonance, in some natural papers, they do the experiment. They couple the atomic BC to the intermediate step and use zero.
Yeah, but this is because you are speaking about Feshbach, optical Feshbach.
Okay.
But this is magnetic Feshbach.
Okay.
So, but for example, in your paper, and you make like stirrup and everything, this is optical. Because the Feshbach, you can make it. I'm working with magnetic Feshbach resonance, but there is also.
So you can direct.
Yeah. It's like the good thing about optical Feshbach is that for a small system they work much better, make all these things, and you know it because you work in it with the stirrup and everything. But for experimental setups and everything, they work with magnetic field. Is much more convenient for big systems.
But you can make your speed limit will be restricted by the magnetic field.
Yeah.
Yes.
Yes. Okay.
The second question is about this Feshbach resonance. When you do the linear run, for instance, this Feshbach runs, so you will cross the zero.
Yeah, you will cross to say you come from the very BCS from no interactive to a really high interactive system.
So in some sense, your G from the negative to the positive, crossing the zero.
You will move A from positive to negative, making the interaction from repulsive to attractive.
And you cannot avoid the atomic loss, because when you crossing the zero point by Feshbach resonance, the atoms will be lost.
Yeah, obviously you will lose atoms because
Then you need speed.
yeah, but you will have losses. Obviously, this will not fix it will not give you like efficient, really like huge, like what I said to Mika. Like there's a lot of losses that come from scattering, inelastic, three body. Like this Hamiltonian is a huge reduction of the problem because the problem still is not solved. But yeah, obviously there will be.
I think the effect of three
No, it's relevant.
it's very.
But you can see because we say if you work with only without free body, you will work with it lambda planar, you can make this, and the results are not good enough to explain. Like you have to add free body because also you have three body collision also can make inelastic or also can form molecules. These other processes that are not Feshbach ramps is free body interaction and also can they are ultra important, but they are important to explain. Obviously, like significant because they have really a lot of detail of the system, so you need to explain it.
Not this. Okay, so you are always talking about the mean field theory and the Gaussian theory. So I thought if you want to apply it back to the mean field theory, it will be easy.
The thing is that this Hamiltonian that we are using is not mean field theory, but you can write it with Gross and Big Bang.
But this Hamiltonian works in the mean field theory.
This Hamiltonian, exactly this, no, but something quite similar. But mean field theory is that the thing that I wanted to use to design a shortcut and make something like of easier calculation, but I realized that maybe the spectroscopic works better for this problem. Like because the thing is that all these Hamiltonian, all these processes are explained by mean field, but the thing is that they are not able to give all the details. Also, it's a really good approximation, but not good enough for the level of the accuracy of the experiment. So first, start to play with beam field, how we can design shortcuts using beam field and get the properties using beam field, because finally we have like it's n to the 4, like this when we are speaking about Fermi cases, we are speaking about 10 to the 4 particles, we are speaking about a lot of particles. So like have all the details of the particles and work independently with the particles in a multi-particle system will be possible. So maybe the beam field looks better.
Yes, that's why I asked this question. I think you may start to design the shortcut in UCOD, which essentially are unlinear to the
Yeah.
and then you can check the go beyond UCOD.
Yeah.
I would expect that the result will be similar.
Yeah.
Because I was checking the shortcut for all the patterns by using the multiple configuration. Go beyond UCOD. I think it will work quite nice.
Then you go to the nested combinations. What's the H and HE that you take?
So.
What do you say?
Yes, so you have your H lambda, right? Which will be
What?
first in the you have your H lambda will be
It's
bosonic plus fermionic, right? So you start with the same.
with a Hamiltonian, delta T is the lambda in our case.
Yes. So your simple Hamiltonian that you initialize is the fermionic phase, and then you go to simple fermionic, and then you go.
Yes. What you make is you have first you have a fermionic gas, a two components fermionic gas, because you need to have spin up, spin down, a mixture of spin up, spin down.
Yes.
You start with this easy to prepare fermi gas, and then you apply the magnetic field and you start to create the boson. So you start from the fermi gas to the bosonic gas.
Okay. So you have, when you do combinations, you have operators that have both bosonic operators and
This. Yeah. The thing is that this is something like, how do you make this experiment?
yeah.
Like, it's the problem that I say, okay, I don't know what to do, but this for simulation works, but not for experiment. This is what, when I read again 4 or 5 times the flocked engineer paper, I realized that we can flocked engineering and it will be much nicer experimentally.
Okay. And the combination between B, comma C is 0. B operator is 0. What's the combination between them?
I can have the notes in this, I can show you later, I don't know.
Okay.
And the days of this I calculated the last thing, I know the days about the computation.
Exactly, this should come in, right? Then if we do this first order operation, the B lambda will be only fermionic, and this will be only bosonic. So I don't know. Maybe I'm missing something.
I think that you have bosonic, no, but the interaction, finally the interaction, you have this term appears with the interaction and the bosonic. You have the B lambda, the H is B dagger B,
Yes.
and the term that survives is the B dagger CC and CC B, C dagger B with
Yes.
different spins, and this gives you this.
Okay.
Because the words, the bosonic is the same term, it disappears, and if you make the computation between the fermionic and the bosonic, it also compute. But the good thing is that if you go to higher orders, you have like you close that error, so you don't have to go to higher order to have all this precision. Okay. Okay, so I hope you enjoyed. If someone is more interested in this topic about Feshbach and all that stuff, let me know.
But really, it's kind of repeating an area is really useful because it will somehow enhance the things and instead for avoiding the point through the Feshbach. Maybe.
The thing that I think that the most what I have to make is right now in the middle of the simulation, like when if I see that there is an answer or not, see this strategy. The flocked engineer probably works well. If not, then we'll have to change the game field. Is the other idea, and have to how to design it using the theory instead of all this using other operators and everything. this right now it's like really soon to say if it will work or not. Probably yes, because and normally works.
Yeah, and you commented that reverse engineering is difficult or something. Why would we use reverse engineering to like convert it to a
You have to reduce the learning and system, which you don't have a dynamics environment. Then you have to find the good answers to do the inverse engineering.
but we can like convert it to mean fit and then
It's not
okay.
Yeah. The thing is that if you go to normal linear, this is we are only using like approximation of one channel. So you can go to the two-level system and everything. But this doesn't works.
Oh,
Like you have to go beyond like the two-level system. We can maybe we can design the other idea the proposal is designing using the non-linear approximation because non-linear approximation explains really quite well all this stuff. Yeah, it's also other stuff that we should make.
everything must be inspired and thought and it's given a workshop. Somehow maybe you can also completely forget this algorithm of structures and network system and industry. Maybe you can start from the semi-classical picture and to derive the true or this is one area. Then you can write on the Lagrangian density and to optimize these things.
The thing is that we have to make actually, we can use music theory to decide the shortcut and everything, but finally we have to go to a more exact Hamiltonian. Like, only can get inspiration from the theory, but if you take the new theory, we will not be precise enough. So you can decide shortcut and everything there, but in the final point you have to go to this Hamiltonian or to more complex Hamiltonian, more specific Hamiltonian, because if not, it's not going to be good enough if you bring the simulation with you. Because it's like for design everything and for getting intuition everything works perfectly. It's really strong. Having like it's a very strong theory. If you want to do the music theory, it's have to fail. If you want to get all the details, and you need a lot of details in collados because they are more precise.